Okay, in this video, we're going to be talking about section 6 out of chapter 5, which deals with rational functions. Rational functions can be quite complicated. There are a lot of details you need to keep track of and a lot of things going on in these functions. So it's possible I may have to split this video into two different parts. We're going to start with what the domain of the rational function is. There are two kinds of exceptions for the domain of a rational function, but they all come from the same place. Basically, the rule is thou shalt not divide by 0. So that is our basic rule, no division by 0. All right? So in words, thou shalt not divide by 0. Now, what does that mean? In order to figure out where the division by 0 is, we need to take the original function and factor the denominator. Even if the factor would cancel, it was there in the original, which means it cannot be allowed in the domain. So anything that causes the denominator to be 0 will be removed from the domain. In this case, I'm going to look at f of x, and I'm only going to focus again on the denominator. I'm going to factor x squared minus 3x plus 2 into the product of two binomials. Since the signs are both the same and they're both negative, I know that 2 has to split as 2 and 1, and this does give me a minus 3x in the middle. The factors are x minus 1 and x minus 2. The solutions that go with those two factors are x equal 1 and x equal 2. I need to throw those numbers out of the domain since they would cause division by 0. So when I think about the domain, I can think about drawing a number line and wanting to leave out the numbers 1 and 2, as in make an empty spot there. So my domain would include all the numbers from negative infinity up to 1, all the numbers between 1 and 2, and all the numbers above 2. So my interval notation will mimic what I have in the picture. Negative infinity on the far left, up to 1. To leave 1 out, I have to do half of an open circle with a round parentheses. Picking up again with the other half of the open circle at 1, then I continue to 2 to get the numbers between 1 and 2. Half of the open circle at 2 with the round parentheses, then open up again at 2 and go to infinity. That's what the domain would look like in interval notation. In the form that you see on the left, what they basically want to know is, okay, I can use any number except, and you just tell it, I want to throw out 1 and I want to throw out 2. Now, what does this produce in the graph when you're looking at these? This is when I do need to consider the numerator. If it's ever in the denominator, it cannot be allowed in the domain. But if it cancels with a factor out of the numerator, it becomes a hole in the graph, like a pothole in the road. In this case, however, the numerator x squared plus 1 doesn't factor, which means that the x minus 1 and x minus 2 factor will remain in f in its reduced fraction form. If the factor's still there in reduced fraction form, then the factor's solution becomes a vertical asymptote. Let me write that in words. If the factor trying to get it to right, remains in the denominator, that's the bottom of the fraction, in reduced fraction form, then the solution of that factor is a vertical asymptote. And we can abbreviate that with VA. Now, what is a vertical asymptote? An asymptote is a line that the graph will get very, very close to. In the case of a vertical line, it gets close to it but cannot touch or cross it. Horizontal asymptotes can be touched and crossed, but never vertical. So in this case, we have a graph that cannot get close to or touch the vertical lines at x equal 1 or x equal 2. On the graph, I will mark off x equal 1 and x equal 2 with dashed lines. That means that whatever this graph looks like, it cannot touch or cross or go over those dashed lines. Those are absolute no touch, never going to happen lines. And that's what zeros in the denominator give you in the graph. So again, if the factor remains, and the factor is x minus 1, in the denominator after you've factored everything and reduced it, then the solution to that factor, and the solution that matches the factor x minus 1 would be x equal 1, then that line, x equal 1, becomes a vertical asymptote in the graph. That's a line that the graph cannot touch or cross, which means that it's going to have to do something maybe like this, where it gets really close, but it can't touch or cross it. Let's move on to the next one and look at the domain of the next problem. On the next problem, I have a much more complicated numerator and denominator. But again, to find the domain, we focus on the denominator only. What would cause the denominator to be 0? Take those values and throw them out of the domain. So first I'm going to take the denominator for f of x, and I'm going to factor it. This looks like something that's quadratic in form, which means that the first term x to the 4th will split as x squared times x squared. Because the constant term is positive, I know the signs are the same, and since the middle term is negative, I know they're both negative. I need two factors of 25 that add to give me 26. It has to be 25 and 1. Those would add to give me a negative 26. Now, notice I'm totally ignoring the numerator. To continue, though, I need to fully factor it, and those are not fully factored. They can be factored more since they're each the difference of two squares. So now I'm going to factor each one as x minus 5, x plus 5 for the first difference of two squares, and x minus 1, x plus 1 for the second difference of two squares. Again, I am totally ignoring the numerator because in this case, the domain is determined only by the denominator. Now in this case, if I were to do this, this means I would need to throw out the solutions that match each of the individual factors. The solution that matches x minus 5 is 5. The solution that matches the factor x plus 5, that's negative 5. The solution that matches the factor x minus 1 is 1, and the solution that matches the factor x plus 1 is minus 1. Now that I have these, I can go ahead and throw those out of the domain. What will it produce in the graph? To know what happens in the graph, I need to take a look at the numerator. Now that I have factored out the denominator fully and thrown all of those zeros out of the domain, now I can look at the numerator and see what effect it will have. So I have tossed out 5, negative 5, 1, and negative 1. The numerator will not affect the domain. Now, when I look at the numerator, I can factor x squared minus 6x plus 5, and it becomes x minus 5 times x minus 1. If I take these and I write them over the fully factored denominator, do you see that you have two pairs of factors that are alike? I have two x minus 5 factors, one in the numerator and one in the denominator. And I also have two x minus 1 factors, one in the numerator, one in the denominator. Dividing these out will give me 1 in each case. That means that the reduced fraction for f will look like 1, since everything canceled out of the numerator, over x plus 5 and x plus 1. This is the reduced fraction. Now, what effect will this have on the graph? I know that I still had to throw out 5 and I still had to throw out 1, but they've canceled because their factors were also present in the numerator. When a factor cancels and disappears completely from the denominator, it becomes a hole in the graph. Let me write that down in words for you now. Okay, let's read this together and then we'll talk about what it means. When a factor cancels from the denominator and numerator, but disappears completely from the reduced denominator, it forms a hole in the graph, like a pothole in the road. The x-coordinate of the hole is the solution of the canceled factor. The y-coordinate of the hole is the value you would get when you plug that x-coordinate into the reduced fraction. Now, a pothole in the road or a hole in the graph is literally what it sounds like. It is where the graph is coming along and then has a hole in it. This is not like a vertical asymptote. This is a hole. A vertical asymptote, on the other hand, is when you have a line and you can neither cross it nor touch it. This is a vertical asymptote. The one on the left is a hole. The one on the left, the hole, is produced by a factor that cancels completely from the denominator. It may or may not still be present in the numerator, but it has disappeared from the denominator. The vertical asymptote is caused by a factor that does not disappear from the denominator. It is still present. Let's look back at our original problem and its reduced fraction form. Our original problem factored was here and here. We've already said that 5 and negative 5, 1 and negative 1 are not in the domain. Notice that after reducing, the factors left in the reduced fraction are x plus 5 and x plus 1. That means the negative 5 and the negative 1, their solutions are vertical asymptotes. So over here, I can label these as vertical asymptotes on the graph. Because the factors x minus 5 and x minus 1 canceled and disappeared from the denominator of the reduced fraction, that means that the 5 and the 1 both produce a hole in the graph. Let's take a look at what this would look like if we were to actually try to factor it on a graph. I have reproduced for you down here a picture of what it looks like from the original unreduced fraction in its factored form to the reduced fraction. We will still have a vertical asymptote at the line x equal negative 5 because the factor x plus 5 is still present. I'll come over to my graph and I'm going to produce a line that is on that spot. So let me draw a line as best I can down x equal negative 5. That is a no touch, no cross zone. I also have a vertical asymptote at x equal negative 1. That is from the factor x plus 1. So I'm going to produce another dashed line going through x equal -1. Now, I have a factor of x minus 5 that canceled and disappeared completely from the denominator. That means I have a hole in the graph, and the x-coordinate of the hole is at 5. How do I find the y-coordinate? To find the y-coordinate, I take the 5 and I plug it into the reduced fraction that you see on the right. This becomes 1 over 5 plus 5 times the quantity 5 plus 1. This gives me 1 over 10 times 6. 10 times 6 is 60. This is 1 over 60. That is really low. What would the hole be at 1? We have a hole at x equal 1 because the factor x minus 1 canceled. To find the y value of the hole, take the 1 and plug it into the reduced fraction. 1 plus 5 would give me 6. And for the second factor in the denominator, 1 plus 1 gives me 2. This gives me 1/12, which means that this hole is at 1/112. These holes are extremely low. That means the holes are practically sitting on the x-axis, but not quite. So at 5 I have a hole, and at 1 I have a hole that's just a little bit higher than that one. Now, I need to determine what the rest of the graph looks like. The graph has to fit between the vertical asymptotes and cannot touch or cross it. It has to split and either walk up the vertical asymptote or down the vertical asymptote. To do this, I can also find the y-intercept. To find the y-intercept, you can replace the x-coordinate with 0 in either the original problem, moving all the way back up here at the beginning, or at any point along the line. That includes into the factored but not reduced fraction, or in the fully factored and reduced fraction. I tend to use the fully factored and reduced fraction. My y-intercept is found by letting the x-coordinate be 0. So I replace x with 0 and I get 0 plus 5 times 0 plus 1. That tells me that my y-intercept is at 1/5. This is slightly higher than the other two, but still really, really low down here. Now this is on the graph and not an empty hole, so I fill that one in solid. Notice that when I was done with the reduced fraction, I had no factors left in the numerator. There is no way, since my reduced fraction has 1 in the numerator, to get the fraction to ever equal 0, which means that this graph can never touch or cross the x-axis. That's where y is 0. Since this graph is slightly above the x-axis at these points, then it has to be skimming along, skipping over that pothole, skipping over that pothole, and getting really close to the x-axis, but never touching or crossing. Now, what could it do in between -5 and -1? It doesn't have a whole lot of choice. Let's show some options. It could be totally below and look something like a parabola. That's one possibility. It could also do a similar thing, but be above the axis. If it were above the axis, then it would also have to be somewhat parabolic in shape. Why can't it be like a cubic and stretch across the x-axis? Again, it cannot because I have 1 in the numerator of the reduced fraction, which tells me it is impossible for that graph to ever hit the x-axis. Now I'm going to try to figure out where it actually is. What's a good test point between -5 and -1? You can use any point you want, but one good test point might be, say, -2. If I plug -2 into my reduced fraction, -2 plus 5 would be 3. That's a positive number, but -2 plus 1 would be negative. That tells me that a positive times a negative is negative, which means at -2 it has to be below, which means that it has to do something like that upside down parabolic shape. Do I know exactly what it looks like? No, but this has to be a fairly close approximation. What about in the last region? In the last region, I know it's not possible for it to touch or cross the x-axis because I have only a constant in the numerator. That means my options for the graph are that it gets sucked in by the vertical asymptote and goes up, or it could get sucked in by the vertical asymptote and be down. It's got to be one or the other. It cannot touch or cross the x-axis. To figure out which one it's got to be, let's take another test point. I'm going to use -6 since it is to the left of -5. If I plug -6 in for x plus 5, I get a -1. -6 plus 1 is also negative, but a negative times a negative gives me a positive. That means that it has to be above the x-axis, so it must be doing something like this. That is roughly what the graph looks like, with 2 potholes in the road at 5 and 1. Let's take a look at the next example. In the next example, we are asked to find the domain, the vertical asymptotes, and the horizontal asymptotes. And we will list any domain restrictions. If I'm looking at this, to find the domain, I only focus again on the denominator. So I'm going to rewrite this by factoring the denominator. First, I remove the common factor of x. That leaves x squared plus 4x minus 5. To continue factoring, I will need to factor the quadratic as the product of two binomials. X squared splits as x and x. I need factors of 5 that subtract to give me 4. It has to be 5 and 1. To end up with a plus 4, I need a plus 5 and a minus 1. That means that x cannot be 0 for the factor x by itself. It cannot be -5 for the x plus 5 factor, and it cannot be 1 for the x minus 1 factor. Now let's put the numerator back in. If I put in 2x plus 3, there is nothing I can take out of that. Since it does not factor, I need to bury the whole thing together, that either the whole factor cancels or none of it cancels. In this case, the numbers I need to throw out from least to greatest would be -5, then 0, then 1. Since none of those factors canceled and disappeared from the denominator, they are all vertical asymptotes at x equal -5, x equals 0, and x equal 1. To find the horizontal asymptote, we play a game I like to call the Bill Gates rule. You won't find this on Google because I made it up. The Bill Gates rule is what happens when you get to infinity and negative infinity. As the numbers get massively large, what happens and what takes over are the highest degree terms in the numerator, the 2x, and the highest degree term in the denominator, x cubed. The further out you get, the more important those terms are and the less important the other terms are. Let's imagine, for example, that I let x be 1 million. If I multiply 1 million by 2, I get 2 million. If I then add 3, adding 3 makes very little difference in the graph. between 2 million and 2,000,003. If I take my 1 million and I cube it, 1 million has 6 zeros behind it. 1 million cubed has 18. While it's true that if I square a million, I will get something with 12 zeros behind it, compared to something with 18 zeros, that's not very big. And the 5 times x will only be 5 million with 6 zeros behind it. This means that the larger the x values get, the more the highest degree terms in the numerator and denominator come to dominate the function and what it looks like. We call these end behavior because they're at the far left and far right of the graph. So end behavior is what happens when x goes to positive infinity and what happens when x goes to negative infinity. And again, I like to call this the Bill Gates rule. This means that the graph of 2x plus 3 over x cubed plus 4x squared minus 5x will approach the graph. It will not equal, but it will approach the graph of 2x over x cubed. If I reduce this, this becomes, oops, hang on a second. This becomes, in reduced form, 2 divided by x squared. When it is a bottom-heavy fraction or a bottom-heavy rational function, meaning that the degree of the denominator is higher than the degree of the numerator, it will approach 0. This means that the x-axis is a horizontal asymptote. Now, what would happen if they had been the same degree? Let's suppose I had 3x cubed plus 2x squared minus 7 divided by 4x cubed plus 11. The end behavior, as I go to infinity or negative infinity, would take the highest degree term on top and bottom and reduce them. This will not equal the graph, but it will get closer and closer to the graph of 3x cubed over 4x cubed, which approaches the horizontal line y equals 3/4. This is what I would call even degree, where the degree of the numerator equals the degree of the denominator. In this case, the horizontal asymptote will be the ratio of the leading coefficients. In this problem, however, our degree in the denominator was 3 and degree in the numerator was 1. Since it's bottom heavy, our horizontal asymptote is the x-axis, y equals 0. Let's take a look at another problem. How can we find the x and y-intercepts of the function? The x-intercepts are given by zeros of the numerator in reduced form. So let me write that down in words. The x-intercepts are the zeros of the reduced numerator. That means you have to go to the fully reduced fraction, find the numerator, and set each factor in the numerator equal to 0. That's where you will find the x-intercepts. For the y-intercept, you can plug 0 for the x-coordinate in any form of the fraction you desire. Let's find the x and y-intercepts on this function. Since x squared plus 3 does not factor, then I can just simply put the whole thing into parentheses. Either it all goes or none of it goes. So my reduced form for the function is going to be exactly what it is in the first place. X minus 5 divided by x squared plus 3. Once I have this, the x-intercept comes from the numerator. I take the factor from the numerator, set it equal to 0, and solve. The x-intercept has to be at 5, 0. The y-intercept comes from allowing the x-coordinate to be 0, or f of 0, which is 0 minus 5 divided by 0 squared plus 3, which would give me negative 5/3. That's the ordered pair 0, negative 5/3. Let's start putting some of the information together. We'll use this to start drawing some graphs. If I'm looking at this one, let's find all the information that we can. We'll start by looking for vertical asymptotes and holes. These are the restrictions on the domain. We'll start by factoring the denominator. 2x squared splits as 2x and x, and the 5 needs to be placed so that I can get a product more than 9, so that when I subtract, I end up with 9. The only way to get a product bigger than 9 is to multiply the 5 by the 2 and the 1 by the 1. This will give me 10x on the outside, 1x on the inside. To get a positive 9, I need a plus 5 and a minus 1. This means that I have to throw out the solution for each of those factors. That means that first I need to throw out of the domain x equal 1/2, and I need to throw out of the domain x equal negative 5. I don't yet know if they're holes or if they're vertical asymptotes until I fully factor the numerator. When I factor the numerator, I would start by trying to split up the 2x squared as 2x and x. There are two ways I can split up the 10. It could be 2 and 5, or it could be 1 and 10. However, I know that the last sign tells me that the signs in the middle of the binomials are the same and they're both negative. That means I need a negative for both. If I'm going to keep their sum below 9, then using 10 and 1 will not work. It has to be 5 and 2. If I multiply the 5 by 2, I again get more than 9. So I will place the 5 so it does not multiply by 2, and the 2 so it does. This gives me minus 5x minus 4x for minus 9x in the middle. Then I look to see if I have exactly the same factor in the numerator and denominator. If I do, and it disappears completely from the denominator, then it must be a hole in the graph. However, although I have similar factors in 2x minus, they're not identical. One of them is 2x minus 5, and the other is 2x minus 1. Therefore, I have no holes in the graph. Both of the zeros of the denominator must be vertical asymptotes. How can I then find the x-intercepts? Take the reduced fraction, take each of the factors from the reduced numerator, and set them equal to 0. Solve for their solutions. That means that I have one x-intercept at 5/2, or at the ordered pair 5/2, 0. Remember that vertical asymptotes are lines, but that x-intercepts are points. The other factor from the reduced numerator is x minus 2. Solving for its 0, I get x equal 2. This is the ordered pair, or the point 2, 0. Now that I have the x-intercepts, how can I find the y-intercept? To find the y, I can go to any of the forms for the fraction, and I can plug in 0 for x. This time I'm going to go to the original problem, way back over on the left, which I'll ring now in red. When I plug 0 in, the first term and the second term in both the numerator and denominator will cancel, and I will simply get that f of 0, and I'm trying to put 0 in the center, f of 0 will give me 10 divided by -5, which is -2. This is the ordered pair 0, -2, which is also a point on the graph, not a line. My next part is to figure out where the horizontal asymptotes are. To find a horizontal asymptote, I want to look at the end behavior. To look at end behavior, I need to decide, is it bottom heavy, or are they even degree, or is it top heavy? In this case, the degree and top, the highest power is 2x squared. The highest degree term on the denominator is also 2x squared. 2x squared divided by 2x squared reduces to 1. This means my horizontal asymptote is the line y = 1. It is a line, not a point. Let's take all the information we've gathered and put it onto the graph to see what else we need to complete. First, I'm going to put on my two vertical asymptotes. I have two vertical asymptotes, one of them at x = 1/2 and one at x = -5. Scrolling down, I have one at x = 1/2, which would be here, and the other one is at x = -5, which is halfway between my -4 and -6. Vertical asymptotes are dashed lines that cannot be touched or crossed by the picture. Now I'm going to put on the x-intercepts. I have two of those, 5/2 0 and 2 0. These are points. 5/2 0 is 2.5 on the x-axis. That's there. The other one is at 2 0, which is right next to it, rather close. To make it show up a little better, I'm going to draw in the picture a little bit, if I can, maybe I can, so that you can see that those are not in fact touching. Now where's the next information that I have? Scrolling back out, I also know that I have the y-intercept at 0, -2, and the horizontal asymptote is the line y = 1. Let's put that information on our graph. The point 0, -2 would be down here, and the horizontal asymptote is y = 1. Let's blow the graph up again so we can see a little better and draw the line at y = 1. Because the horizontal asymptote is end behavior, I do not need to draw it until I get to the far left and far right of the picture. It does not enter into play here in the center of the picture because it is end behavior as x goes to infinity or -infinity. Scrolling back out just a little bit, how am I going to fit the graph? It is clear that it has to get close to this horizontal line. It has to touch here at 2.5, touch again at 2, and then get close to this vertical line. Let's take a test point between, say, well, do we even need a test point? What has to happen between 2.5 out to here? Doesn't it pretty much have to touch and go along that graph? Now, there could be something happening between 2 and 2.5. Between 2 and 2.5, I need to analyze the signs. To do that, let's reproduce our fraction in reduced form. I want to know what happens between x equal 2 and x equal 2.5. A number between 2 and 2.5 would be x equals, say, 2.25, or even x equals 2.2. It's not a great number, but we're kind of stuck with it. Now we're going to imagine what would happen if we were to plug this number into the reduced fraction. I am not concerned with the actual value. I'm only concerned with whether it's positive or negative, so I know that it goes below the x-axis or above. If I were to double 2.2, I would get 4.4, but 4.4 minus 5 would still be negative. If I were to take 2.2 and subtract 2, however, I would get a positive 0.2, so it would be positive. If I double 2.2, I have 4.4 minus 1 would still be 3.4, which is still positive. If I add 2.2 to 5, I get 7.2, which is still positive. The combination of all four of these signs will be negative. Because it's negative, I know that between these numbers, the graph has to go down into the negative region and turn around and come back to hit it 2. I don't know exactly how low it goes, and I won't be able to figure that out until I take Calculus 1. What about in the next region? In the next region, I know from looking at my graph that it has to come close to this vertical line. It never touches the x-axis again, but it could cross over and go up, or it could bounce off and go down. To determine that, let's take a test point between 1 and 2. If I take a test point between, or 1/2 and 2 rather, my vertical asymptote is at 1/2. If I take a test point between 1/2 and 2, a good test point would be x equals 1. So if I test x equals 1 and I plug it into the reduced fraction, 1 times 2 is 2, minus 5 would be negative. Again, I'm not looking for an actual number. I'm looking for above the x-axis or below, positive or negative. 1 minus 2 would give me a negative as well. In the denominator, if I doubled 2 and subtracted 1, I would still have a positive. If I add 1 to 5, I have a positive. This time, the combination of all four signs gives me a positive, which tells me that it crosses over the line and skims along that vertical asymptote and goes up forever. What are the next regions I need to consider in my graph? Clearly, the y-intercept is below the x-axis at -2. Since it doesn't cross the x-axis again, it cannot cross and go up. It has to skim along the vertical asymptote to the right and go up and then come back down and skim along the other vertical asymptote on the left. It never crosses the x-axis, so it cannot follow the upper halves of those vertical asymptotes. What other regions do I need to consider? Let's keep going on the other side of that vertical asymptote at -5. If I'm down here, there's nothing else to break up the number line. I have to get close to this horizontal line at y equal to 1 and close to the vertical line at x equal -5. Whatever the graph does, it has to more or less do something like this, where it skims along the vertical asymptote going up and skims along the horizontal asymptote going to the left. That is a rough picture, very rough, of what it looks like. Let me produce the actual graph and we'll see how close we got on Desmos. Now you can see the picture of our drawn graph on the left and the picture that Desmos produced here on the right. You'll notice that these are in fact quite close together. The only thing that you can't really see on the Desmos picture is the detail where it dips below the line. In fact, it's such a small dip that I had to scroll way in to get it to show up. And even then, it was barely below, really a small amount. When we hand draw them, we tend to exaggerate so that we can see what's going on in that region. Let's take a look at the next problem. The next problem is very similar. We're simply going to do one more problem like this, and then I want to take one look at a slanted or oblique asymptote. We're going to go through our steps again, trying to find the vertical asymptotes and holes first by looking for restrictions on the domain. This is going to start by needing to factor into the numerator and denominator. So in this case, I'm going to take the x squared minus 25 and I'll factor it first into x plus 5 and x minus 5. I know that 5 and negative 5 will not be in the domain. I don't know whether they're vertical asymptotes or holes until I get the numerator factored fully. To factor x squared minus 8x plus 15, I need to write it as the product of two binomials. The signs in the middle will be the same and both negative, and the factors of 15 that add to give me negative 8 are negative 5 and negative 3. That means I do have the same common factor x minus 5 in the numerator and denominator. When I fully reduce and cancel that, I will be left with x minus 3 over x plus 5. This means that my vertical asymptote, which is a line, will come from the uncancelled, still present x plus 5 factor and its solution, x equal negative 5. There is a hole in the graph, and the hole is present at the solution of the factor that cancelled. This is more like a point, only it's a missing point. The hole came from the cancelled factor x minus 5, this cancelled, and that gives me a hole at 5, but not a line. To find the y value at the hole, I need to plug the 5 into the reduced fraction. This will give me 5 minus 3 divided by 5 plus 5, or 2/10, which reduces to 1/5. To find the x-intercept, I return to the reduced fraction, take the factors from the reduced numerator, and set them equal to 0. I take the reduced numerator equal to 0. X minus 3 equals 0 tells me that I have an x-intercept when x is 3, but x-intercepts are points and not lines. To find the y-intercept, I simply need to allow the x-coordinate to be 0 in any of the versions of this problem. It might be easiest to return to the unfactored version since it will be the ratio of the constants. 15 divided by negative 25 should reduce when dividing by 5 to a negative 3 over 5. What about my horizontal asymptote? My horizontal asymptote is usually one of the last things to find. This is my end behavior. This is determined by the highest degree term in the numerator, which is x squared, and the highest degree term in the denominator, also x squared. Since that reduces to 1, that means my horizontal asymptote is the line y equal 1. If I fill in the information, I have a horizontal asymptote at y equal 1, a vertical asymptote at x equal negative 5. I have no slant asymptote because the degree of the numerator and denominator were the same. My x-intercept is at 3, 0, and my y-intercept is at 0, negative 3/5. They didn't ask here, but I will ask on the test, where is the hole? and the hole in the graph is going to be at 5/1/5. Once you have all the information, we can put this onto the graph. Let's pause and do that now. Let's take a look at the information we have to work with. X-intercepts at 3, 0, Y-intercept -3/5. To put this on the graph, I'm going to stretch it out. X-intercept here at 3, 0, Y-intercept at -3/5, which is about 0.6. Since this is 0.1, -0.6 is about there. The next piece of information that we can use came from the horizontal asymptote at 1 and the vertical asymptote at -5. A horizontal asymptote at 1 only applies to the edges of the picture, way to the far right and way to the far left. The vertical asymptote we found was -5. We will draw a vertical dashed line along x = -5. This is a no-touch, no-cross zone. What other pieces of information did we get? We also got a hole. Our hole is at 5/1/5. This is the last piece of information we got from our analysis of this function. We're going to put the hole at 5/1/5. That means it is a little bit above the x-axis, but not by much. 5/1/5 would be right around here, above but not on the x-axis. It is empty because it's a hole. Now I know that the graph has to get close to the vertical line here on the left at -5 and close to the horizontal line as it moves off to the right. Since it clearly has to skip over the hole, it's got to come up like this and then get close to this point here. Since it goes from the X-intercept down to the Y-intercept, it can't bounce and go up. It has to cross and go down. Once it's below the axis, it never crosses again because there are no other X-intercepts. That means that the graph has to keep going down and get close to the vertical asymptote at -5, headed towards -infinity. Now what can I do over on the other side of that vertical asymptote? I have to get close to the horizontal line, y = 1, and close to the vertical line, x = -5. That will draw in the graph like this. If you produce this graph on Desmos, you will see something very close to what we have here. Desmos will not show you the hole unless you click on it. If you click on the spot where the hole is supposed to be, it will tell you that it is not defined or does not exist at that point. There's one more problem type we want to look at before we end this section. The last problem type I want to look at is what's called a removable discontinuity. The removable discontinuity is the hole that I've been dealing with all the way along, but this problem is important for another reason. This problem also has a slanted asymptote. In fact, it is a slant asymptote. Let's take a look at this one and see what happens when we factor the top and the bottom. When I look at this, in factored form, I can do nothing to x - 3, so I put it in parentheses. It all goes or none of it goes. What about the numerator? I know that 3 will not be allowed in the domain of the function, but I don't yet know if it's a whole or a vertical asymptote. To figure that out, we need to factor the numerator. Factoring the numerator, I get x and x. I have a 3 and a 1, and when they subtract, I end up with -2. That means I need -3 and +1. Notice that we have factor of x - 3 in the numerator and the denominator. That means that that factor will cancel. Because it cancels, that means that it must be a hole in the graph at x equals 3. So we will have a hole, which is similar to a point, in the graph when the x-coordinate is 3. To find the y value at the hole, take the 3 and plug it into the reduced fraction. In this case, our reduced fraction is simply x plus 1, so the hole will be present at 3 plus 1, or 4. In fact, this graph is the graph of the line x plus 1, but it has a hole at 3, 4. Let's look and see what that would look like. Putting on the graph, I can graph the line x plus 1 by having it cross the axis at 1 with slope of 1. When I get to x equals 3, however, I need to remember that it's a hole at 3, 4. So if I'm moving across, this means that when I'm at 2, the y value should be 3, but at 3, I have a hole in the graph there at 4. That means from there out, it looks just like the line, but right there at 3, 4, I have a hole or a pothole in the graph. Let's do one more example with a better slanted asymptote. Let's take a look at this last example so you can see what an oblique asymptote really is. In this particular problem, I start out the same as I have every other time. There are values that are not allowed because they cause 0 in the denominator. Let's take our denominator and factor it fully. In this case, all I can do is remove the common factor of 2, leaving me with x plus 1 as a binomial factor in the denominator. This means that my domain will include all real numbers except the solution for the factor x plus 1, which is x equal negative 1. I will have to throw out x equal negative 1. So my domain will be all reals except negative 1. What about the numerator? I don't yet know is this going to be a vertical asymptote or a hole until I factor the numerator. I'm not sure that x squared minus x plus 4 factors. We can try it, but I think you will find that it in fact does not factor and is in fact prime, meaning has no factorable form. In this case, the x plus 1 cannot cancel, which means that the vertical asymptote becomes the line x equal negative 1. On my graph, I will draw a line down x equal negative 1. This is a no-touch, no-cross, invisible force field. What other pieces of information do I have? I can't set the numerator easily equal to 0 and solve, but I can set it equal to 0 and solve. If I set it equal to 0 and solve, I'm trying to find the x-intercepts. So I will take my x squared minus x plus 4, set it equal to 0. Because it did not factor, I either have to use the quadratic equation or completing the square to find any x-intercepts. When I solve, I get x equals, the opposite of b would be positive 1 plus or minus the square root of negative 1 squared minus 4 times a, which is 1, times c, which is 4, all divided by 2 times a, which is 1. When I simplify, I get 1 plus or minus the square root of 1 minus 16. I now know I'm in trouble. This leads to a negative underneath the radical, which tells me it has an imaginary part that's not 0. Because of this negative, I know that there are no real x-intercepts, and the only solutions are complex with a non-zero imaginary part. This means that it does not touch or cross the x-axis anywhere along the line. Now I can find the y-intercept by allowing x to be 0 or just taking the ratio of the two constants. My y-intercept will have to be when x is 0, and it will occur when the y value is 2. Plotting that point on the graph would give me that point there. I've done the x-intercept, the y-intercept. I looked for holes and didn't have any. I did have one vertical asymptote. The only thing left for me to find is the end behavior. This time I have an issue. My end behavior looks at the highest degree term in the numerator divided by the highest degree term in the denominator. This time it is a top-heavy fraction. When it is a top-heavy fraction, it means that the end behavior does not follow a horizontal line, but will instead follow some other shape. We will only study ones that are exactly 1 degree higher. That is, the degree of the numerator is exactly 1 higher or 1 more than the degree of the denominator. The degree of the numerator is 2, and the degree of the denominator is 1, and that meets that qualification. When that happens, when they are precisely 1 apart, with the higher one being in the numerator, then the asymptote at the ends is a line. To find the line, we're going to perform long division on the original problem, x squared minus x plus 4 over 2x plus 2. Let me put this down below so that we can see what it would look like. Reproducing the picture, I need to now do long division with that. Or in this case, you could use synthetic if you wanted to solve for the solution that goes with the 2x plus 2. I choose to do long division this time. X squared minus x plus 4 divided by 2x plus 2. First, I estimate. When I estimate, I am actually taking the highest degree term in the dividend, x squared, and dividing by the highest degree term in the divisor, 2x. Because ours will be precisely 1 apart, you will only have to do this once. My estimate is going to be 1/2 x, or x divided by 2. I put this value up in the quotient. Then I multiply my estimate by my original divisor. This will give me half of 2x is 1x times another x is exactly x squared. Those should always match. 1/2 x times 2 would give me 1x. My next step is to subtract the polynomial by putting the product in parentheses and changing the signs. When I change the signs, they both become subtraction. X squared minus x squared is 0, but negative x minus x is a negative 2x. Then my last step is to bring down. When I bring down, I'm going to bring down everything. Again, we'll only need to go through these steps a couple of times since ours will be precisely 1 higher. We will repeat by finding our new estimate, dividing negative 2x, the new highest term in the dividend, by the highest term in the divisor, 2x. My new estimate, this is step 1 again, will be negative 1. I put minus 1 up in the quotient. Then I repeat step 2, which is to multiply. Multiplying negative 1 by 2x gives me negative 2x. Negative 1 times 2 gives me negative 2. Then I repeat step 3, subtract. When I repeat step 3, I have to put the product in parentheses with a negative on the outside. Change the signs and circles so you know which ones to use. This made them both plus. Negative 2x plus 2x is 0. 4 plus 2 is 6. 6 is a constant, which has degree 0, which is smaller than degree 1, which is what 2x has. This becomes my remainder. Now that I'm done, how did this help me find the oblique or slanted asymptote? The word that I'm using is oblique, meaning squashed. It's also called a slanted asymptote because it is, in fact, not a horizontal. It is a slanted line. The slanted asymptote is the line given by the quotient part, ignoring completely the remainder. I take only the quotient part out of the long division or synthetic division, and I ignore the remainder. Now I'm going to come up to the picture we had before and graph the line 1/2 x minus 1. Coming back to my graph, I need to graph 1/2 x minus 1. This will be minus 1 here, which I can put with an x, and 1/2 x means slope 1/2. I rise 1, move to the right 2, and I'm using x's for my line. 1/2 x minus 1 is the one that goes up 1, right 2, up 1, right 2, or down 1, left 2, down 1, left 2. Repeating this process until I can get most of the way across the picture. Up 1, right 2, and down 1, left 2. I can now draw a dashed line for the slanted or oblique asymptote. Pulling it in just a bit, this becomes my no-touch, no-cross zone. Now, what does my actual graph have to look like? I know that the graph has to get close to the blue slanted asymptote and close to the red vertical asymptote. It also has to hit at 2, 0. If it's going to hit here, then it has to hit here, skim up along the vertical asymptote, come down from there, and then skim out along the slanted asymptote. On the other side of that vertical asymptote, I cannot draw it in this region because it never crosses the x-axis. That means it has to fit into this wedge right here. These are the two pieces of that graph. This is the end of this video, and I hope this helps you to understand how to graph and analyze rational functions.